A single particle of light, traveling from Earth, needs more than 4 years to complete its journey to our nearest stellar neighbor. At such a velocity, the simple act of crossing our own galaxy expands into a voyage of 100,000 years. We exist within a kind of cosmic confinement, held back by barriers constructed from the laws of physics themselves. But an intriguing question has emerged. What if those barriers could be bent? Some scientists are now exploring a theoretical method that might allow a spacecraft to travel at 10 times the speed of light, potentially transforming journeys of centuries into manageable decades. This line of inquiry hints at a future where warp bubbles could manifest in laboratories, and where the energy demands for such travel might shift from the realm of the impossible to something merely extraordinary. Our exploration of this potential breakthrough begins with where we are now. The fastest vehicle humanity has ever constructed, the Parker Solar Probe, moves through space at an astonishing 190,000 miles per hour. This speed seems remarkable until one considers that it would still require 70,000 years to arrive at the closest star system. Such a trip would have needed to begin during the last ice age to be ending in our distant future. Humanity finds itself caught in a velocity trap that conventional rockets alone cannot overcome. Light itself travels at 670 million miles per hour, yet even at this ultimate speed, it takes 4.5 years to span the distance between our world and Proxima Centauri. The Milky Way galaxy measures 100,000 light-years from one edge to the other. A simple calculation reveals that crossing it would be an endeavor lasting for millennia. Every star that glimmers in the night sky represents a destination that our current technology makes completely inaccessible within a single human lifespan. The Voyager probes, which departed in 1977, are now just under 14 billion miles from their origin. They have been voyaging for nearly 5 decades, yet they have still not fully escaped the gravitational hold of our own solar system. For them, the stars remain an impossibly remote prospect. We are, in a sense, cosmic infants, crawling at a time when we need to be sprinting. The stark reality is that space is not merely large, its scale seems to actively defy our ambitions. The gulfs between stars are so profound that even a ship moving at 99% of light speed would turn interstellar travel into a multi-generational undertaking. It might be your distant descendants who finally witness the arrival at a destination you selected. Every propulsion system we have ever engineered functions on the same fundamental concept: pushing something out the back to move forward. Chemical rockets achieve this by burning fuel, while ion drives expel electrified particles. Nuclear thermal engines would blast superheated gas. All of these systems are bound by classical physics, and all of them move at a snail's pace compared to the cosmic distances we hope to conquer. Scientists refer to this limitation as the tyranny of the rocket equation. The more fuel a vessel carries, the heavier it becomes. The heavier the vessel is, the more fuel is required to move it. This creates a difficult feedback loop, where fuel tanks would need to be larger than entire cities just to attain a small fraction of light speed. Simply adding more thrust only contributes more weight to the problem. We have dispatched robotic explorers to Mars, landed rovers on faraway moons, and even taken photographs of the very edge of our observable universe. Despite these triumphs, we are still confined to our own celestial backyard, gazing at fences we are unable to climb. The closest world that might harbour life is situated 4 light-years away. With the technology we possess today, reaching it would necessitate some 25,000 years of uninterrupted flight. A fundamental change is needed. The cosmos is populated with billions of potentially habitable planets, yet we can hardly reach the nearest celestial body in our own neighbourhood. What is it that chains us to this painstakingly slow existence? The answer can be found within the equations of one man, formulated more than a century ago. When Albert Einstein published his theory of special relativity in 1905, he inadvertently constructed an invisible prison around humankind. His work revealed a startling truth. Nothing that possesses mass can ever reach or surpass the speed of light. The universe itself enforces this decree through the very fabric of space and time. The underlying reason is deceptively simple. As any object accelerates and gets closer to the speed of light, its mass increases. This is not a minor change. The faster it travels, the heavier it becomes on an exponential scale. A spacecraft nearing light speed would eventually possess more mass than entire galaxies. Propelling it even 1 mile per hour faster would demand an astronomical surge in energy. This establishes a cosmic paradox. Energy is required to accelerate mass, but the act of accelerating increases that mass, which in turn demands even more energy, further increasing the mass. This cycle spirals toward infinity at the precise moment the light speed threshold would be crossed. In essence, the universe permits you to approach this limit, but never to touch it. Einstein described it as a universal speed limit. For more than 100 years, his mathematics have remained unshaken by every experimental test. Particle accelerators can smash atoms together at 99.99% of light speed, and in doing so, they confirm his predictions with unnerving precision. The objects truly do become heavier. Time for those objects genuinely does slow down. These rules appear to be absolute. Scientists have made every effort to discover a loophole. They have explored exotic methods of propulsion and calculated trajectories that use gravitational assists from planets. They have even proposed the idea of generation ships, where entire societies would be born, live, and pass away during the long voyage. None of these ideas alter the fundamental issue. Einstein's equations have locked the door, and conventional physics has not been able to produce the key. Physicists consider these principles to be inviolable. To break them would be to break the principle of causality itself, creating paradoxes where effects could precede their causes. It would unravel the logical framework that holds reality together. The universe, it seems, would sooner collapse than allow an object with mass to exceed the speed of light. The phenomenon of time dilation introduces another layer of difficulty. Even if one could somehow attain 99% of light speed, time would pass differently for the traveler than for everyone on Earth. A journey that feels like 10 years to the crew might correspond to decades or even centuries back home. You would return to a world where everyone you once knew was long gone, and their great-grandchildren were now elderly. The sense of isolation would be total. Length contraction adds another bewildering dimension. At such extreme velocities, space itself appears to compress in the direction of travel. Distances seem to shrink. A trip that should take years might feel as though it lasts only months for the occupant of the ship. While decades pass for the outside world, the universe warps around fast-moving objects in ways that challenge our everyday intuition. For generations, the scientific community accepted this as the final word. The speed of light was the absolute limit, and nothing could escape it. This concept became a cornerstone of every physics curriculum on the planet. To violate it seemed as impossible as constructing a square circle or proving that 2 + 2 = 5. Yet, a handful of scientists refused to concede permanent defeat. They began to pose a different kind of question. What if our entire understanding of movement is flawed? To accelerate even a small spacecraft to the speed of light would require more energy than is currently available in every fuel tank, battery, and power plant on Earth combined. Even if you were to amplify that immense figure by 1 billion, the total would remain inadequate. The daunting mathematics that govern this problem are both confirmed and absolute. As an object's velocity rises, its kinetic energy increases alongside it. When approaching the speed of light, these energy needs don't simply climb, they grow exponentially. A vessel with a mass of just 1 ton would require something in the order of 9 × 10⁻16 joules to attain light speed. This amount is equivalent to the entire annual energy production of all human civilization. It would all be expended in mere seconds for the sole purpose of accelerating a relatively small craft. Nuclear fusion, the very process that powers the stars, represents the most energy-dense fuel source we can imagine. And yet, even if we could convert the entire mass of a large asteroid into pure energy, it would only propel a moderately sized starship to a small fraction of light speed. What we face are not simply difficult engineering challenges, but rather fundamental physical barriers. Project Daedalus, a concept formulated in the 1970 seconds, envisioned using fusion rockets to achieve 12% of the speed of light. This goal may sound modest, but the design reveals the true scale of the undertaking. The proposed craft would consist mainly of fuel tanks, each the size of a skyscraper, holding 50,000 tons of deuterium and helium-3. By comparison, the payload section designated for cargo and crew would be incredibly small. Even this colossal ship would require 2 decades of travel just to arrive at the outer reaches of our closest neighboring star systems. Antimatter engines could, in theory, offer a better ratio. When matter and antimatter make contact, they annihilate one another, converting their mass into energy with 100% efficiency. This makes it the most effective fuel theoretically conceivable. The issue lies in our ability to create it. We can currently produce antimatter only a single particle at a time through the use of enormous accelerators. Containing it necessitates magnetic bottles that themselves consume vast amounts of power. With our existing technology, generating enough antimatter to power a single interstellar journey would require thousands of years. Some physicists have suggested the use of solar sails, which are gigantic, reflective sheets propelled by the pressure of light from stars. These vessels would need no fuel whatsoever, only an immense amount of patience. The acceleration they provide is exceptionally slow, measured in fractions of inches per second, but it accumulates over many years. To reach even 10% of light speed would demand decades of uninterrupted acceleration. Furthermore, such a sail would need to be miles in diameter, extraordinarily thin, and yet durable enough to avoid tearing. Every conventional method of propulsion confronts the same essential obstacle. The faster one wishes to travel, the more fuel is required. The more fuel carried aboard, the heavier the ship becomes. The heavier the ship is, the more energy is needed to accelerate it. Engineers refer to this as a cycle of diminishing returns. It is a cosmic paradox. Chemical rockets are limited to approximately 5 miles per second. Ion drives might attain speeds of 20 or 30. Nuclear thermal engines could potentially reach 50. The most optimistic designs for fusion propulsion top out around 3,000 miles per second, which is still only 1% of the speed of light. Our efforts are akin to trying to move a mountain by tossing small stones at it. This energy trap is not merely about constructing bigger engines or discovering a more potent fuel. It is a fundamental constraint woven into the fabric of reality. Einstein's equations make it clear that for any object with mass to reach the speed of light, an infinite amount of energy would be necessary. Infinite, by its very definition, means impossible. No amount of clever engineering, no technological breakthrough, and no degree of human will can alter that physical law. However, this trap is only present if one adheres to the conventional rules of motion. What if movement itself is not what we perceive it to be? The Earth could be facing a terminal decline, and we have no other place to go. This sobering thought is a constant preoccupation for researchers, because an examination of our cosmic vicinity reveals a stark truth. Every other planet within our solar system is a lethally hostile environment. Mars, our nearest potential alternative, is a frozen desert where temperatures can fall to negative 225 degrees Fahrenheit. Its atmosphere consists of 96% carbon dioxide and is so thin that standing on its surface is equivalent to being at an altitude of 19 miles on Earth. The extremely low pressure would cause a person's blood to boil. Planet-encompassing dust storms can last for months, and without a protective magnetic field, which Mars lost billions of years ago, the surface is constantly bombarded by cosmic radiation. Venus presents an even more forbidding picture. Underneath its dense cloud cover, the surface temperature is 860 degrees Fahrenheit, which is hot enough to melt lead. The atmospheric pressure there is comparable to being 3,000 feet beneath the ocean on Earth. The atmosphere is composed primarily of carbon dioxide, with clouds of sulfuric acid. The probes that have been sent to Venus survived for less than 2 hours before they were crushed and melted. Thriving there is not just difficult, it is an impossibility. The gas giants provide no solid surface to stand on at all. Jupiter, Saturn, Uranus, and Neptune are essentially massive spheres of hydrogen and helium, characterized by crushing pressures and winds that can reach 1,000 miles per hour. Their moons offer slightly more viable, though still frozen, airless, and deadly, options. Titan, the largest moon of Saturn, has lakes of liquid methane and a dense atmosphere. This might sound promising, but the surface temperature is a constant minus 290 degrees Fahrenheit. An unprotected person would freeze solid within seconds. Europa, which orbits Jupiter, may conceal liquid water beneath miles of ice, but gaining access to it would mean drilling through that immense frozen shell in one of the most radiation-intense environments in the solar system. Mercury experiences extreme temperature swings, from 800 degrees on its sunlit side to minus 300 degrees in its shadows. Our own moon lacks an atmosphere and water, and it endures the same radiation that strikes Earth, but without the benefit of a protective magnetic field. Every single celestial body in our solar system is either excessively hot, excessively cold, or entirely devoid of the basic necessities for human life. The concept of terraforming these worlds remains purely theoretical. Even the most hopeful projections indicate that making Mars even marginally habitable would take thousands of years and depend on technologies that have yet to be invented. We would need to thicken its atmosphere, warm its surface, reactivate its magnetic field, and generate breathable air. Each of these steps poses a nearly insurmountable challenge. Earth is not just our home. For the foreseeable future, potentially for millions of years, it is our only viable home, even with unlimited technological capabilities. This means that if climate change, an asteroid impact, or another catastrophe renders Earth uninhabitable, humanity has no alternative plan. It is imperative that we reach beyond our solar system, not merely for the sake of exploration, but for our very survival. The problem is that these potentially habitable worlds are light years away. Proxima Centauri b orbits within its star's habitable zone, just 4 light years from us. The TRAPPIST-1 system has 7 Earth-sized planets, with 3 that could potentially support life, located 39 light years away. Kepler 452b, which bears a strong resemblance to Earth, is situated 1,400 light years from here. These worlds could be our future homes, but with our current technology, they are as unreachable as if they existed in another dimension. This is the reason why faster-than-light travel is not a mere convenience. The impulse to seek out new worlds feels almost instinctual, a kind of evolutionary imperative. To reach them, however, requires us to challenge the most basic speed limit known to physics. Our telescopes have revealed a stunning catalogue of more than 5,000 confirmed planets orbiting other stars, with dozens of them located in the so-called habitable zone, where conditions might allow for liquid water. We have the technology to see these distant worlds. We can determine their dimensions, their likely composition, and the shape of their orbits. It's even possible to estimate their surface temperatures and analyze the makeup of their atmospheres. The one thing we cannot do is go there. Proxima Centauri b is a world that particularly captures the imagination of astronomers, as it embodies everything we desire in a planet and everything that remains beyond our abilities. At a distance of just 4.2 light-years, this exoplanet circles a red dwarf star within its habitable zone. There is a chance it possesses oceans. It could potentially support life. Some of the initial data even hints that it may have a protective magnetic field to shield it from harmful radiation. According to scientific estimates, the planet receives a level of energy from its star that is comparable to what Earth receives from the Sunday. The discovery of the TRAPPIST-1 system in 2017 generated a new wave of wonder. Here, 7 planets, all roughly the size of Earth, orbit a small, cool star only 39 light-years from us. Remarkably, 3 of these worlds are situated firmly inside the habitable zone. Computer simulations indicate that they could possess atmospheres, complex weather patterns, and stable climates. The presence of liquid water on their surfaces is not merely a possibility, it is considered likely. Another world, Kepler 452b, often called Earth's cousin, circles a star that bears a striking resemblance to our own. It absorbs only about 10% more energy than Earth does, which suggests its surface temperatures could fall within a range suitable for life. This planet is 1,400 light-years away, and finding it was like discovering a long-lost sibling on the far side of an ocean that can never be crossed. Discoveries like these continue to accumulate. Each year adds dozens of new potential worlds to our lists. We find planets with dense atmospheres and others with day-night cycles much like our own. We see rocky planets with the ideal mass to retain their air without creating crushing surface gravity. Our catalogues now include frozen worlds and lava worlds, ocean worlds and desert worlds. The galaxy is teeming with possibilities, and yet, every last one of them is completely inaccessible. Even our nearest candidate, Proxima Centauri b, would take 40,000 years to reach using our fastest current spacecraft. A journey to the TRAPPIST-1 system would last 600,000 years. Reaching Kepler 452b would require 25 million years of uninterrupted travel. At this scale, the numbers cease to be travel times and become geological ages. It is as if we are observers looking through a window at magnificent landscapes we can never walk upon. Astronomers are capable of describing the atmospheric gases of planets dozens of light years away, but we are unable to dispatch even a tiny probe to study them within any kind of practical time frame. The James Webb Space Telescope can detect the chemical fingerprints of water vapor and oxygen in the air of alien worlds. Still, the act of physically visiting those places remains firmly in the realm of fantasy. This limitation creates a frustration that extends beyond simple scientific curiosity. These planets represent potential new homes for humanity in the distant future. They could serve as a refuge should Earth ever become uninhabitable. They might contain ecosystems for us to study, resources for us to utilize, or perhaps even intelligent life with whom we could communicate. Everything we hope to learn, and every place we might need to go, lies just beyond our reach, separated from us by an immense barrier of distance and physics. Radio communications, moving at the speed of light, would require years to cross the gap to these worlds. If we were to detect a sign of intelligent life today and send a reply, their response would not reach us for decades. Any conversation would have to unfold over the course of generations. Physical travel appears to be an impossibility unless we fundamentally rethink our entire approach to motion. This impasse suggests that perhaps we should stop trying to propel ourselves through space and instead find a way to move space itself. Miguel Alcubierre was a graduate student with a fascination for Star Trek when he set out to determine if a warp drive could function within the known laws of physics. In 1994, he published a paper whose mathematics was so unexpected yet so technically sound that it made professional physicists pause and reconsider. The concept he proposed, the Alcubierre drive, does not work by accelerating a ship through space at all. Instead, it generates a bubble of warped spacetime around the vessel. This bubble causes space to contract in front of the ship and to expand behind it, which in turn creates a wave that propels the bubble forward. The ship, nestled inside this bubble, remains stationary relative to the space immediately surrounding it, meaning it feels no forces of acceleration. A useful analogy is that of a surfer riding an ocean wave. The surfer is not actively swimming or generating their own velocity. They are simply carried along by the motion of the wave, standing still on their board as the ocean provides all the momentum. Alcubierre's equations outlined how a spacecraft could ride a wave of space-time in a very similar fashion. The ingenuity of the idea lies in its exploitation of a loophole in Einstein's theories. General relativity states that nothing with mass can travel times through time-space faster than the speed of light. That principle remains intact. But Einstein's work never claimed that space times itself times is bound by that same limitation. In fact, cosmologists are well aware that space is expanding faster than light at the far edges of the observable universe. This expansion is the very mechanism that allowed our universe to grow from an infinitesimal point to its current vastness in just under 14 billion years. If space is already capable of exceeding the cosmic speed limit, the question becomes whether we can harness that capability. Alcubierre's mathematics demonstrated that one could, in theory, generate a region of negative energy density ahead of a ship to make space contract, while using positive energy behind it to make space expand. The bubble containing the ship would be pushed forward by this asymmetrical distortion of space-time. No conventional thrust would be required, and no g-forces would be felt. The ship would simply ride the wave. His paper sent ripples of excitement through the world of theoretical physics. It was a landmark moment, presenting for the first time a mechanism for faster-than-light travel that was constructed using the accepted equations of general relativity. This was not speculative fiction. It was peer-reviewed mathematics published in a respected physics journal. According to the known laws of the universe, the method appeared to be technically permissible. Other scientists quickly moved to check his work. They confirmed that the mathematics was solid. It was theoretically possible to warp spacetime in this manner without violating principles like causality or breaking relativity. While the energy needed would be absolutely astronomical, it would be finite. This was a significant improvement over traditional propulsion, which would require a literal infinity of energy to reach the speed of light. The Alcubierre drive could, in principle, achieve any speed imaginable, 10 times the speed of light, 100 times, or even 1,000. The bubble is not moving times through time-space, so the strange effects of relativity, such as time dilation and length contraction, would not apply. The crew inside the bubble would experience the normal passage of time. They would not age more slowly than the people they left behind. They would not perceive distances as being compressed. Within the bubble, physics would remain completely ordinary. Alcubierre himself later said that he had never actually anticipated that the concept would prove to be mathematically viable. It began not in a laboratory, but as a recreational exercise in mathematics, conceived by a physics student drawing inspiration from a favorite television program. His calculations, however, unexpectedly pointed to a real possibility concealed within the very structure of space-time. It was as if reality itself contained a hidden shortcut, a fundamental principle waiting to be exploited. Of course, the engineering challenges of constructing such a device would make the theory seem simple in retrospect, but a conceptual door had been opened. What once seemed impossible now appeared merely extraordinarily difficult. Space-time is not a featureless void. It is a tangible fabric, a medium that can be bent, stretched, twisted, and made to ripple. Every object with mass creates a depression in this fabric, much like a heavy ball placed on a taut sheet. That indentation is what we perceive as the force of gravity. Albert Einstein first described this relationship more than a century ago, and it has been verified through countless observations since. The satellites of the Global Positioning System must constantly adjust for the fact that time passes slightly faster for them in orbit than it does on Earth's surface, as they are situated higher up in our planet's gravitational well. Similar effects have been measured using hyper-accurate atomic clocks on airplanes. Black holes represent the most extreme example, warping space-time so profoundly that beyond the event horizon, no escape is possible. The Alcubierre drive takes this fundamental concept of warped space and proposes a way to control it. Rather than passively submitting to the natural curvature of gravity, a spacecraft would artificially generate a localized bubble of distorted space around itself. This warp would compress space-time in the direction of travel and expand it behind the vessel, creating a wave that carries the bubble forward. The ship itself would remain stationary within this bubble, never actually moving through the space around it. Instead, space would be moving around the ship. This might sound like a minor distinction, but its implications are profound, allowing for a complete circumvention of Einstein's ultimate speed limit. The theory of relativity places firm restrictions on how fast an object can travel times through time-space, but it imposes no such limits on how fast space itself can expand or contract. The difference is critical, because all the paradoxical consequences of near-light speed travel, such as time dilation, length contraction, and the need for infinite energy simply vanish when the object in question is not technically in motion. Inside this warp bubble, the laws of physics would operate as expected. Crew members could walk about the vessel, enjoy a cup of coffee, or play a game of cards, all while experiencing the passage of time at precisely the same rate as everyone back on Earth. There would be no twin paradox, where an astronaut returns home younger than their own children, nor would there be any of the relativistic visual distortions that would plague conventional high-speed travel. The bubble effectively insulates its occupants from the extreme space-time manipulations occurring at its boundary. The wave itself could theoretically travel at any speed. Miguel Alcubierre's original paper suggested that 10 times the speed of light would be a relatively straightforward velocity to achieve. More recent theoretical work has explored variations that could reach 100 or even 1,000 times the speed of light. At such speeds, the journey to Proxima Centauri would shorten to a matter of weeks. An entire crossing of the Milky Way galaxy could be accomplished within a single human lifetime. To an outside observer, the warp bubble would present a strange spectacle. Light would struggle to escape the region of highly compressed space at the front of the ship, rendering it partially invisible. The expanding space at the rear would stretch light waves so dramatically that they would be redshifted into the radio spectrum. It is also possible that the bubble would emit exotic forms of radiation as it moved, leaving a visible wake through the fabric of space-time. From within the ship, the view would be equally surreal. Space ahead would seem compressed, making distant stars and galaxies appear much closer than they truly were. The light from these stars would be shifted in color as it passed through the distorted warp field. Looking backward, space would appear to be stretching away into infinity, though one could still see the point of origin, its light simply shifted to different wavelengths. The mathematics that describe this process are deeply complex, involving tensor equations and the principles of differential geometry. Yet the core idea remains one of elegant simplicity: to surf on a wave of space-time, allowing the universe to do the moving while the ship rests comfortably inside a pocket of normal reality. The key to achieving this is the creation of an asymmetric curvature in space-time. This, in turn, requires the ability to manipulate the energy density of space in ways that border on the magical. And this brings us to the single greatest obstacle to the entire concept. Alcubierre's design for a warp drive depends on a substance that, as far as we know, does not exist: exotic matter with negative mass and negative energy density. This is not the same as antimatter, which is very real and simply annihilates with regular matter in a release of energy. This theoretical substance is far stranger, a material that would repel instead of attract, push instead of pull, and essentially make gravity operate in reverse. Normal matter curves space-time inward, creating the gravitational wells that keep planets in their orbits and cause apples to fall from trees. Exotic matter, by contrast, would curve space-time outward, generating a kind of gravitational hill that actively pushes things away. It represents the conceptual opposite of everything we understand about how mass and energy behave in our cosmos. The question remains, does negative mass exist? It has never been directly observed. No experiment has ever measured it, no laboratory has ever created it, and no evidence has ever been found of it occurring naturally anywhere in the universe. It persists only as a theoretical possibility, a mathematical curiosity permitted by the equations of general relativity that nature itself has seemingly chosen not to create. The sheer quantity of this material required for a warp drive only compounds the problem. Alcubierre's original paper calculated that one would need a quantity of negative mass equivalent to the total mass energy of the planet Jupiter just to warp space around a small vessel. Jupiter has a mass more than 300 times that of Earth. The energy required to convert such a vast amount of normal matter into exotic matter, assuming such a process is even possible, would be far beyond anything humanity could ever hope to generate. Critics immediately focused on this requirement. They argued that while the mathematics were internally consistent, a theory that relied on non-existent materials was fundamentally useless. It was, they suggested, no different from designing a perpetual motion machine that runs on a fantasy fuel. The physics might be sound on paper, but the necessary ingredients are pure fiction. Some researchers have attempted to find ways around this problem. Could intense electromagnetic fields be used to generate the necessary negative energy density within a vacuum? Perhaps quantum fluctuations could be carefully manipulated to produce the desired effect. Dark energy, the mysterious force that is causing the expansion of the universe to accelerate, does display properties similar to negative pressure. Could it somehow be harnessed or concentrated? These questions have fueled decades of theoretical research but have yielded no practical solutions. Creating a sustained, large-scale region of negative energy density appears to violate several fundamental tenets of physics, including what are known as the energy conditions in quantum field theory. The universe may even have built-in safeguards to prevent such concentrations, precisely to avoid the paradoxes and violations of causality that they might permit. A very faint glimmer of hope can be found in the Casimir effect. This phenomenon occurs when two uncharged metal plates are placed exceptionally close to one another in a vacuum. Quantum fluctuations in the space between the plates create a region with a slightly lower energy density than the surrounding empty space. The space between the plates contains less quantum vacuum energy than the surrounding void, a condition that technically qualifies as negative relative energy density. Even though its absolute value remains positive, the resulting effect is measurable, confirmed, and entirely real. This leads to an intriguing question about whether this principle could be scaled up. If it were possible to create and control Casimir-like effects on a massive scale, one might be able to generate the space-time distortions necessary for a warp bubble without relying on exotic matter whatsoever. The energy would, of course, have to originate from some source, but the physics involved would be known and established rather than dependent on hypothetical constructs. It is at this point that Dr. Harold White enters the narrative, guiding the conversation from pure theory into something closer to experimental science. Dr. White dedicated years to researching propulsion physics at NASA's Johnson Space Center in Houston. There, his team managed a laboratory focused on investigating unconventional propulsion ideas, the kind of frontier science that might draw skeptical looks from colleagues, but can sometimes lead to revolutionary discoveries. In 2011, White published a new set of calculations which proposed that the energy demands for an Alcubierre drive could be significantly lower than previously estimated. His revised mathematics indicated that by optimizing the warp bubble's shape, the energy requirements might be reduced by several orders of magnitude. Instead of needing exotic matter equivalent to the mass of Jupiter, the new figure was closer to several hundred kilograms. While still exotic and unavailable, this adjustment shifted the concept from the realm of physical impossibility to that of extreme difficulty. Then, a remarkable development occurred in 2021. White's team was conducting studies on the Casimir effect with specialized instruments built to measure nanoscale forces between metallic plates. Their objective was not to create a warp bubble. Instead, they were exploring if Casimir forces could be harnessed for spacecraft attitude control, a piece of fundamental, not revolutionary, research. During one of their experimental runs, the sensors registered something extraordinary, a detectable warp in spacetime at the nanometer scale. The data precisely matched the theoretical predictions for the signature of a minuscule warp bubble. They had, quite by accident, generated the exact spacetime geometry described by Alcubierre, albeit on a scale millions of times smaller than what would be needed for actual propulsion. The team repeated the experiment on multiple occasions, and the effect remained consistent and measurable each time. What they were observing was not an instrumentation error or random quantum noise. It was a genuine, repeatable distortion of spacetime, created by manipulating the Casimir effect. A warp bubble, microscopic yet real, had materialized in a laboratory on Earth. The implications of this discovery sent quiet shockwaves through the propulsion physics community. The geometry of a warp drive was no longer just a theoretical idea. It was something that could be created, measured, and studied experimentally. The challenge of scaling a nanoscale warp bubble up was now framed as an engineering problem, not a barrier of fundamental physics. Naturally, critics called for verification. Before anyone could claim definitive proof, other laboratories would need to reproduce the findings. The necessary equipment is highly specialized and costly, so independent confirmation would take time. Some physicists put forward alternative explanations for White's sensor readings, suggesting possibilities like electromagnetic interference or a misinterpretation of quantum effects. In science, skepticism is always a healthy response. Yet, White's team had meticulously calibrated their instruments, accounted for all known sources of potential error, and documented their procedures with great care. The data appeared to be solid. What was particularly compelling is that the effect manifested precisely when theory predicted it should, and disappeared when the conditions were altered. This kind of correlation points toward a real phenomenon rather than a simple measurement artifact. In the wake of these findings, NASA quietly provided additional funding for White's lab. Other government agencies also began to show interest. Private aerospace firms started to recruit propulsion physicists to look into the generation of warp fields. A new kind of race had begun, not to immediately construct a warp drive, but to first understand if scaling up from the nano to the macro level was even feasible. The problem of exotic matter still posed a significant hurdle. Even with the reduced energy needs, a negative energy density was still required to produce the asymmetric spacetime curvature. While White's experiments demonstrated that Casimir effects could yield a warp-like geometry, it was only at a tiny scale using minuscule energy manipulations. The leap from nanometers to meters would require a billion-fold increase in scale. Nevertheless, a crucial psychological barrier had been broken. Warp bubbles were now a part of reality, not just concepts on a page. This realization changed the entire landscape. Suddenly, other research groups began to revisit old papers on warp drives, searching for details that might have been overlooked. Perhaps the solution had been hidden in plain sight all along. The Casimir effect itself can seem like magic, but it arises from one of the most peculiar confirmed truths about our universe: that empty space is not truly empty. According to quantum field theory, the vacuum is a turbulent sea of virtual particles that constantly pop into and out of existence. These particles exist for infinitesimally brief moments, borrowing their energy from quantum uncertainty before vanishing, as if repaying a debt to the cosmos. While these virtual particles cannot be observed directly, their effects can be detected. They produce a subtle background energy that permeates the entirety of space. Under normal circumstances, this quantum vacuum energy is uniform, exerting an equal pressure in all directions, which is why it goes unnoticed. However, in 1948, the Dutch physicist Hendrik Casimir predicted that something unusual would occur under specific conditions. He theorized that if you were to place two uncharged metal plates extremely close to one another, these plates would limit which virtual particles could exist in the gap between them. Only particles with wavelengths smaller than the gap could manifest in that space. Outside the plates, however, virtual particles of all wavelengths could exist without restriction. This situation creates a distinct imbalance. There is more quantum pressure from the outside pushing the plates together than there is from the inside pushing them apart. The result is that the plates attract each other with a force that can be measured. Despite having no electrical charge and no conventional interaction, they are being pressed toward each other by a disparity in quantum vacuum fluctuations. The force itself is incredibly small, only becoming noticeable when the plates are separated by a distance less than the width of a human hair, but it is entirely real and has been measured in countless experiments. The Casimir effect serves as proof that negative energy density can exist in nature. The space between those plates possesses less quantum vacuum energy than normal empty space, which technically counts as a negative energy relative to the surrounding vacuum. This is a critical insight, as it suggests that exotic matter might not be a prerequisite for warp drives if one could find a way to amplify and control Casimir-like effects. The experiments led by Harold White put this principle into practice through the meticulous arrangement of capacitor plates into highly specific geometric patterns. His team successfully established zones where the energy of the quantum vacuum was different from its baseline state. These subtle variations in energy density produced a slight warping of space-time, generating distortions that were physically measurable. The resulting distortion was infinitesimal, yet undeniably present. To scale this effect up, however, involves confronting monumental difficulties. The Casimir force diminishes profoundly with distance. If the plates are moved apart by even a tiny amount, the phenomenon simply disappears. Generating negative energy densities akin to the Casimir effect over spans of meters instead of nanometers would demand entirely new methodologies. Such an endeavor might rely on exotic materials or quantum technologies that are not yet developed. Some physicists have put forward the idea of using metamaterials, which are artificially engineered structures capable of bending light and electromagnetic fields in unconventional ways. Others have theorized that techniques from quantum computing could grant precise dominion over vacuum fluctuations. A few more radical thinkers have even posited a potential link between dark energy, the enigmatic force driving the universe's accelerating expansion, and vacuum energy states that could be manipulated. Even with the reductions offered by Casimir effects, the energy requirements continue to be breathtaking. It is still necessary to generate and sustain steep energy gradients along the boundary of the warp bubble. This calls for power sources that vastly exceed anything we can currently produce. While nuclear fusion could potentially supply enough concentrated energy, harnessing it with the precision needed to sculpt space-time is a challenge of an entirely different order. Nevertheless, a conceptual door had been opened. The need for exotic matter might not be absolute after all. It appeared that real, observable physics could potentially generate warp-like distortions in space-time. The journey from a nanoscale proof of concept to a full-scale spacecraft application seemed incredibly long and fraught with uncertainty. But a path did exist. This signified genuine advancement, moving beyond mere theoretical conjecture. The subsequent major step forward would emerge from an unforeseen source, listening to the cosmos for evidence that another intelligence may have already surmounted these obstacles. When Miguel Alcubierre first performed the calculations for his warp drive's energy needs, the results were apocalyptic. The concept demanded the conversion of the entire mass of Jupiter into pure energy, which then had to be somehow condensed into exotic matter. This is equivalent to approximately 2 times 10 to the power of 30 kilograms, or about 1.9 times 10 47 joules of energy. To put that into perspective, the most powerful nuclear weapon ever detonated unleashed around 2.1 times 10, 17th joules. The warp drive would require that bomb's total energy output multiplied by a trillion. These figures effectively halted any serious consideration of the idea. While the mathematics was certainly elegant and the concept was permissible under the laws of relativity, a requirement for more energy than multiple stellar cores relegated the entire notion to a theoretical curiosity. Building such a device seemed as plausible as constructing a physical ladder to the moon, but Harold White perceived something crucial within the equations. The energy demands were heavily dependent on two specific variables: the thickness of the warp bubble's wall and the overall geometry of the bubble itself. Alcubierre's original model had employed relatively thick walls and a simple spherical form, primarily because it simplified the mathematical work. The critical question became, what if those parameters were optimized? White suggested reconfiguring the bubble into a toroidal shape, similar to a donut, instead of a sphere. He also calculated that causing the bubble wall's thickness to oscillate, rather than keeping it static, could drastically lower the energy requirements. The mathematics involved grew substantially more intricate, but it was manageable for modern computers. When he processed the numbers for this optimized model, the outcome was astonishing to everyone in the field. The energy requirement plummeted from the mass of Jupiter to an equivalent of something closer to 500 kilograms of exotic matter. This was still a tremendous and exotic amount, but it was many orders of magnitude more plausible than the initial figure. This quantity of mass is comparable to that of a small satellite. It could theoretically be contained within a spacecraft, eliminating the need for a planet-sized energy source. Subsequent refinements have continued to brighten the outlook. Various research teams have proposed different bubble geometries, including elongated ellipsoids, figure 8 configurations, and nested shells with varying densities. Each new optimization has incrementally reduced the energy demands. Some recent studies propose that it might be possible to achieve the effect with only several dozen kg of negative energy density, provided the geometry is perfectly calibrated. These advancements were achieved solely through mathematical optimization, discovering more efficient methods to warp spacetime that yield the same propulsive effect with a smaller energy investment. The process is analogous to how engineers enhanced rocket efficiency over many decades by refining nozzle shapes, fuel-to-oxidizer ratios, and combustion chamber designs. The underlying physics did not change, but intelligent optimization unlocked superior performance. A truly exciting development arose when researchers recognized that sustained exotic matter might not be necessary at all. Certain models indicate that one could use conventional energy to create fleeting pockets of negative energy density through quantum effects. These regions would be maintained just long enough to produce thrust before being allowed to collapse, then recreated in a cycle. This can be compared to internal combustion engines, which operate on pulsed fuel ignition rather than a continuous burn. Such a pulsed warp drive concept could theoretically be powered by advanced fusion reactors or antimatter annihilation, sidestepping the need for storing exotic matter. Exotic effects would still be required, but only transiently and in a controlled fashion. This reframes the problem, shifting it from a challenge of material science to one of precision engineering. The question remains whether these optimizations can truly work in practice. The mathematics seems robust and has been verified by multiple independent physicists. However, mathematics only reveals what could be possible within the framework of known laws. Whether the physical universe will cooperate with these theoretical models is a question that can only be answered by building and testing actual hardware. Still, reducing the energy needs from the mass of Jupiter to the mass of a satellite marks undeniable progress. It has transformed the warp drive concept from an impossibility into something that is merely extraordinarily difficult. Sometimes, that distinction is what makes all the difference. Meanwhile, other research teams were tackling the problem from a completely different perspective. The Brazilian physicist José Natario examined Alcubierre's equations and identified areas for potential refinement. In 2002, he published an alternative model for a warp drive that employed different geometric strategies to obtain similar outcomes. The Natario drive, as it came to be called, generates space-time distortions using a modified tensor field configuration. Some physicists contend that this design is inherently more stable than Alcubierre's original proposal. The essential difference is found in the way the warp bubble interacts with normal spacetime at its boundary. A fundamental issue within the Alcubierre model is located at the bubble's boundary, where the fabric of space would experience a severe and sudden shift from a compressed condition to a normal one, and then into an expanded state. These sharp divisions would demand incredibly high concentrations of energy and could generate hazardous radiation or disruptive gravitational effects. An alternative concept, put forward by Notario, aimed to soften these abrupt changes. His model proposes a more gradual distortion of spacetime that is distributed across a much larger volume, which consequently lowers the peak energy density needed at any single point. The contrast is much like that between a sheer vertical cliff and a gently sloped hill. While both produce a change in elevation, the slope is fundamentally more stable and less difficult to traverse. This geometric rethinking has profound implications for the drive's theoretical stability. The intense energy gradients in Alcubierre's design might be vulnerable to quantum instabilities or even spontaneous disintegration, whereas a smoother distribution could prove far more robust. The Notario drive also seems to lessen certain secondary phenomena, like the Hawking radiation that could otherwise emerge at the warp bubble's edge. While the total energy requirements for the Notario model are on par with optimized versions of the Alcubierre drive, the engineering obstacles they pose are distinct. The challenge becomes how to generate a gentler, yet more spatially vast, warping of spacetime. This objective might actually be more attainable using phenomena like the Casimir effect or the manipulation of electromagnetic fields, since it doesn't require extreme energy densities focused on specific points. The compromise, however, involves a significant leap in mathematical difficulty, as Notario's equations are even more daunting than Alcubierre's already complex formulations. The field tensors at play require a deep expertise in differential geometry to be fully comprehended. This complexity is a primary reason why popular science tends to focus on Alcubierre's model. It remains far simpler to visualize and describe. Some theorists now suggest that the most viable solution might ultimately be a synthesis of both frameworks. A hybrid design could employ Notario's smooth boundary geometry for improved stability, while simultaneously incorporating Alcubierre's oscillating bubble walls to help mitigate the enormous energy demands. Such composite models could potentially offer a way forward that captures the strengths of each approach. In a separate line of research, a team at the University of Göttingen in Germany has been investigating whether warp geometries with entirely different topologies might be more efficient. Instead of bubbles or toroidal shapes, they considered if helical warp fields or even braided spacetime structures could perform better. The field of possibilities broadens immensely once spacetime is treated not as a static backdrop, but as a pliable medium that can be molded in inventive ways. At present, these geometric inquiries are purely theoretical exercises. No one has built even a microscopic prototype of an Notario drive to verify that the mathematics aligns with physical reality. Nevertheless, the expanding diversity of proposed models is a sign that warp drive physics is maturing from a single speculative notion into a genuine area of study with multiple competing ideas. This variety is an indicator of a healthy scientific field. It is plausible that different geometries would be best suited for different missions. A short-range warp jump might use one type of configuration, while a long-haul interstellar voyage could depend on another. Just as aircraft are built in many different forms according to their purpose, so too might warp drives eventually come in a range of specialized designs. This line of thinking naturally led researchers to a fascinating question. Could another civilization in the universe have already solved this puzzle? And if so, might we be able to detect the evidence of their technology? We understand that gravitational waves are ripples in space-time that are produced when massive objects accelerate with extreme violence. Colliding black holes, merging neutron stars, and supernovae all broadcast these disturbances across the cosmos at the speed of light. We now possess the ability to perceive them using observatories like LIGO and Virgo, which can measure space-time distortions smaller than a proton's width. In 2024, a research group at Germany's University of Potsdam developed a clever idea. They reasoned that if warp drives work by bending space-time, Their operation must also create gravitational waves. The resulting pattern would be entirely distinct from the waves generated by natural astronomical sources. A moving warp bubble, they determined, would produce a very specific signature in the gravitational wave spectrum that is based on its shape and speed. The researchers then conducted simulations to show exactly how these warp drive signatures would appear to our detectors. They calculated the frequencies, amplitudes, and polarization patterns that would be created by different warp drive designs. With these theoretical templates, they began to search through existing gravitational wave data for a match. To date, nothing has been found in the current archives, but this is hardly surprising. The science of gravitational wave astronomy is still very young. LIGO, for example, only achieved its first detection in 2015. We have barely started to listen to the universe in this remarkable new way. The advanced detectors that are planned to come online in the next decade will be substantially more sensitive, able to hear much quieter signals and distinguish more complex patterns. If any advanced culture within a few billion light years has developed warp drive capabilities, we might detect their ships moving through space by the gravitational ripples they leave in their wake. These ripples would propagate outward at light speed, forming expanding shells of distorted spacetime that would eventually pass over Earth. The implications of such a finding are staggering. We could learn that faster-than-light travel is physically possible, not by inventing it ourselves, but by observing others who already use it. Each detection would provide clues about how they constructed their drives, revealing details about the energy signatures, the bubble geometries, and the propulsion systems. It would be analogous to discovering alien tracks and, from their patterns, deducing the principles of their locomotion. Some critics argue, however, that any civilization capable of building warp drives would likely take measures to avoid detection. It is conceivable they would shield their gravitational signatures or use modified warp geometries that minimize any detectable emissions. Perhaps they also refrain from traveling through populated galactic regions at warp speed to prevent revealing their presence. But even a very careful civilization might leave behind occasional traces. A single unshielded warp jump, an emergency maneuver, or the signal from an older, primitive warp drive from their early history could be all that is needed. We would only need to observe one clear example to prove that the concept works in reality. The search also extends beyond just gravitational waves. A warp bubble, traveling at extreme speeds through interstellar gas and dust, should create shock waves and unique radiation signatures. High-energy particles accelerated at the bubble's edge might generate gamma rays or bursts of cosmic rays. Optical telescopes could also play a role by looking for the characteristic red and blue shifting of light around a moving warp field. For now, there have been no confirmed detections. The universe appears to be silent on these frequencies, at least in the data we have so far been able to examine. The fact that we have not yet detected a signal does not mean nothing is there, especially since our serious listening efforts have only spanned a few years with equipment of limited sensitivity. Imagine, for a moment, the confirmation of the first unambiguous warp drive signature. Such an event would resolve two of humanity's most enduring questions in a single stroke. Are we truly alone, and is faster-than-light travel physically achievable? This discovery would fundamentally reshape physics and could accelerate our own warp drive research by decades, as we would know with certainty that the universe permits this technology. Until that day, the search continues. More detectors are brought online each year, our algorithms become more refined, and the techniques for analysis grow ever more sophisticated. If alien warp drives are indeed leaving their impressions on spacetime itself, it seems inevitable that we will eventually find them. The profound question then becomes what we would do next. The concept of reverse engineering alien technology may sound like science fiction, but it reflects a pattern repeated throughout human history. When gunpowder first arrived in Europe from China, its new users did not require a complete understanding of its chemistry to make use of it. They could analyze the mixture, experiment with different ratios, and ultimately replicate the technology. This same process has been applied to countless innovations, from the secrets of making steel to the design of semiconductors. Detecting the gravitational wave signatures from an alien warp drive would offer an incredible advantage, providing us with direct observations of a working model. The intricate patterns within those waves could reveal the geometry of the warp bubble, the the distribution of its energy, the timing of its propulsion, and its complete acceleration profile. We could measure all of this from the outside without ever needing to see the internal mechanics of the device itself. This would present engineers with a vast and complex puzzle known as an inverse problem, where the goal is to deduce the input by carefully analyzing the output. This approach is fundamental to modern engineering, where external measurements are often used to infer internal structures. A medical CT scan operates on the very same principle, reconstructing a three-dimensional view of our anatomy from a series of two-dimensional X-ray projections. The foundational work by the German team has already prepared us for this kind of analysis. They have created an extensive library of simulated warp signatures so that when a genuine detection occurs, algorithms can rapidly match the observed patterns to theoretical models. It is a system for identifying a drive's design by comparing its unique gravitational fingerprint to a catalogue of known possibilities. Some thinkers raise ethical concerns about potential treaty violations or a breach of galactic etiquette. If advanced civilizations are deliberately hiding their warp signatures, they ask, should we respect that desire for privacy? Others argue that acquiring knowledge is not the same as theft. We would not be stealing their vessels or acting aggressively. We would simply be learning from observations that are theoretically available to anyone. The technological gap, however, might be enormous. A civilization using warp drives could be thousands or even millions of years more advanced than our own. Their grasp of fundamental physics might incorporate principles we have not yet discovered. In that scenario, attempting to reverse engineer their technology could prove impossible if it relies on science that is currently beyond our comprehension. And yet, perhaps not. Warp drives, wherever they are, likely obey the same universal laws of physics. General relativity functions the same on alien worlds as it does here. If they have found a way to generate negative energy density or to manipulate the curvature of spacetime, those mechanisms should be understandable to us once we observe the evidence. The mathematics would surely be difficult, but likely not incomprehensible. History offers a reason for optimism. When the Antikythera mechanism, a stunningly advanced astronomical calculator from 150 BC, was discovered, those who found it could not begin to fathom its purpose. Yet, through modern analysis, we eventually unraveled its functions and its brilliant engineering, knowledge compounds, and each new clue accelerates further discovery. Detecting even one confirmed alien warp signature would prove that the technology works in physical reality under actual operating conditions. That confirmation alone would be invaluable. It would end the long-standing debates about whether various theoretical objections are truly insurmountable. The universe would have provided us with an existence proof. Funding for warp drive research would almost certainly skyrocket overnight. Governments and private companies would enter a race to develop working prototypes. The scientist or organization that successfully deciphers the alien technology would instantly become the most important entity on Earth. The geopolitical implications are staggering to consider. However, a development path based on observation also carries significant risks. What if the signatures reveal catastrophically dangerous side effects? It is conceivable that warp bubbles inflict cumulative damage on the local fabric of spacetime. Perhaps they create hazardous radiation or destabilize quantum fields. We might discover the very reason why other civilizations use their drives sparingly or avoid certain regions of space. Still, the potential rewards seem to dwarf the risks. Learning how to achieve faster-than-light travel from alien examples could save humanity centuries of dangerous experimentation. We could potentially skip the trial and error phase and move directly to proven, effective designs. Of course, all of this assumes that aliens exist, use warp drives, and do so in ways we can detect. This leads to a truly unsettling thought. What if they are already here, observing us as we struggle with these very calculations? The prospect of faster-than-light travel terrifies some physicists because it appears to be inextricably linked to time travel, which in turn creates logical impossibilities that threaten the consistency of reality itself. The grandfather paradox illustrates this perfectly. If you were to travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But if you were never born, you could never have traveled back in time. This means your grandfather does meet your grandmother, so you are born, and you do travel back, creating an infinite loop with no consistent resolution. Warp drives could potentially enable similar paradoxes on cosmic scales. If you travel faster than light between two reference frames that are moving relative to each other, you could theoretically arrive at your destination before you left, at least according to certain observers. The mathematics becomes complicated quickly, involving concepts like closed time-like curves and violations of causality, but the conclusion seems inescapable. Within the framework of relativity, faster than light, movement and time travel are connected. Some physicists argue this connection proves faster than light travel must be impossible. The universe, they contend, cannot permit causality violations because they create logical contradictions. If effects could precede their causes, then nothing would make sense. You could receive answers before asking questions, die before being born, or prevent events that have already happened. Reality would simply collapse into incoherence. A fascinating concept from the physicist Stephen Hawking, known as the chronology protection conjecture, suggests that some undiscovered law of physics prevents time travel even when theoretical equations seem to allow it. According to this idea, whenever an attempt is made to build a time machine or move faster than light, subtle quantum phenomena or other physical mechanisms would step in to forbid the creation of paradoxes. In this view, the cosmos has a built-in mechanism to preserve its own logical coherence. Other scientists, however, note that warp drives might possess a natural design that circumvents such paradoxes. The region of space contained within the warp bubble travels faster than light relative to the surrounding universe, yet nothing inside the bubble ever locally violates the light speed barrier. Information is unable to travel backward in time through the bubble, a consequence of the bubble's ability to isolate its interior from external frames of reference. Consider trying to transmit a signal from inside a warp bubble to the outside. That signal would have to pass through the bubble's boundary, a frontier that separates two profoundly different regions of space-time. It is possible that this very act of crossing would enforce causality, blocking any transmission that could lead to a paradox. The bubble, in effect, would serve as a barrier to isolate and prevent any problematic flow of information. Another intriguing detail is that warp drives would need a constant supply of energy to sustain the distortion in space-time. This power would likely be generated by fusion or antimatter reactions occurring in the present moment. It would be impossible to supply power retroactively to a warp bubble that has already ceased to exist. This inherent directionality in time might be another factor that naturally prohibits travel into the past, even if the vessel moves faster than light. Some theoretical models offer a different solution, suggesting that multiple timelines or parallel universes could resolve any paradoxes. In this scenario, if you were to travel back and alter a past event, you would not change your original timeline but would instead create an entirely new one that branches off from that point in time. Your own history would remain untouched, but you would be unable to return to it. This many worlds interpretation elegantly removes logical contradictions, though it does so by introducing an infinite number of parallel realities. This concept resonates with certain interpretations of quantum mechanics, which already hints at something similar through processes like measurement and entanglement. The universe might just naturally diverge into parallel branches with every choice, and warp travel could simply be a way of accessing these other branches. You would not be changing your own past. You would be visiting a parallel version of it, where things happen differently. None of this has been confirmed, of course, as we are speculating about technologies that are purely hypothetical, using incomplete theories to guess at their behavior. The honest answer, however, is that we do not know if faster-than-light travel would create paradoxes, because we have never done it. The universe may have protective systems in place that we have not yet conceived. What seems clear is that successfully building a functional warp drive would bring these profound questions into sharp focus. Either paradoxes would arise, forcing us to discover new physics to account for them, or they would not, revealing that causality protection is woven into the fabric of space-time. Either result would constitute a revolutionary leap in our understanding. A fear of paradoxes, then, should not be a barrier to investigation. Scientists have an ethical duty to move forward with caution, but also to seek knowledge about the fundamental limits of reality. If warp drives are ultimately shown to be impossible because of causality protection, that discovery in itself would be a deep insight into the structure of the cosmos. One of the most poignant and difficult consequences of traveling near the speed of light with conventional propulsion is a phenomenon known as time dilation. Einstein's equations predict that for any object moving at high velocity, time passes more slowly compared to a stationary observer. This effect becomes more and more extreme as one approaches the speed of light. At 99% of light speed, time for you would slow down by a factor of 7 compared to people on Earth. This means a voyage that feels like a 10-year journey to the crew could correspond to 70 years passing back home. You would return having barely aged, only to find that your friends and family are now elderly or gone, your children are older than you, and society has been transformed into something unrecognizable. The sense of isolation would be profound and irreversible. You would become a person out of time, living a strange existence where your personal clock is no longer synchronized with the world you left behind. The classic illustration of this is the twin paradox. In this thought experiment, one of two identical twins embarks on a high-speed space journey while the other stays on Earth. Upon the traveler's return, they are measurably younger than their sibling. Their biological age, counted in heartbeats and cell divisions, is genuinely different. This is not a mere trick of perception or a subjective experience. Time itself has passed at different rates for each of them. Experiments in particle accelerators provide constant proof of this reality. Unstable particles that should decay in microseconds are observed to last significantly longer when they are accelerated to 99% of the speed of light. Their own internal clocks effectively slow down. The universe is indifferent to how strange this may seem to us. The mathematics is sound, the predictions align with observations, and these rules are enforced without exception. For any interstellar mission that relies on conventional propulsion, this temporal separation is an unavoidable reality. A trip to a star 50 light-years away might take 100 years as measured by clocks on Earth, even at very high speeds. The travelers themselves might only experience 20 years, provided their velocity is great enough, but everyone they ever knew would still have aged by a full century. The concept of a generation ship is one attempt to address this, by essentially embracing the long duration of the voyage. Multiple generations would be born, live, and die during the journey. Time dilation thus becomes a moot point, but this solution introduces its own set of daunting challenges. It would require maintaining social order for centuries, preserving the mission's purpose across generations who never chose their fate, and preventing technological and cultural divergence that could make a return to Earth an impossibility. What is remarkable about a theoretical warp drive is how it completely bypasses this entire set of problems. This is because the ship inside a warp bubble is not actually accelerating through space at relativistic speeds. As a result, time dilation does not apply. The bubble itself is what moves, carrying a pocket of undisturbed spacetime along with it. Within this bubble, the passage of time would remain perfectly synchronized with time back on Earth. You could journey to Proxima Centauri in a matter of weeks, return, and discover that only weeks have passed for everyone. This represents one of the most significant advantages of a warp drive, even beyond its incredible speed. It preserves the crucial temporal link to home. You could leave for years and know with certainty that you would return to the same era you departed from. Your personal relationships would remain intact, and your knowledge would still be relevant. You would not become a temporal refugee, displaced from your own time. Crew members would live and age normally throughout their journey. There would be no need for suspended animation, no complex generational planning, and no psychological trauma from being disconnected from your own time. The mission's timeline could be measured in years that are meaningful on a human scale, rather than across entire epochs of civilization. This feature also makes warp travel a more practical and economically feasible endeavor. A corporation that funds an interstellar mining operation, for instance, needs to see a return on its investment within a horizon measured in decades, not over the course of centuries. For any government or institution planning missions to colonize other worlds, the prospect of waiting generations for simple feedback is unworkable. A key appeal of warp drives is their potential to bring interstellar endeavors into a time frame that aligns with human plans and motivations. The absence of time dilation also elegantly resolves profound problems with causality. When time flows at a consistent rate for everyone, the natural order of cause and effect is preserved. This stability means one cannot manipulate relativistic time differences to generate paradoxes or transmit information into the past through clever navigation between reference frames. Naturally, this all rests on the assumption that warp bubbles function as the theories predict. Should they possess unforeseen effects on the flow of time, these certainties would dissolve. But based on current models, warp travel seems to offer genuinely rapid transit without the temporal complications that make relativistic journeys so difficult, both psychologically and socially. The ability to escape time dilation alone would make warp technology a worthy pursuit, even if its speeds were no greater than conventional propulsion. However, there is another challenge that a warp drive circumvents, one that is far more immediately lethal. Using traditional propulsion to accelerate a human being to extreme speeds would prove fatal long before reaching any significant fraction of light speed. The forces at play are simply too powerful for biological matter to withstand. During a rocket launch, astronauts typically endure forces around 3 times Earth's gravity. Fighter pilots, pressed into their seats with what feels like triple their own weight, can momentarily tolerate up to 9 times Earth's gravity in extreme maneuvers before they lose consciousness. To achieve even 1% of the speed of light within a practical time frame would call for a sustained acceleration thousands of times more powerful than the gravity of Earth. Under such conditions, the human body would not simply feel heavy, it would disintegrate. Bones would be crushed under the immense compression, and blood vessels would burst. The brain would be slammed against the interior of the skull, resulting in death that would be both instantaneous and absolute. Some works of science fiction have imagined solutions like acceleration couches, which would be filled with liquid to support the body from all sides and distribute the stress. This concept might offer some help during moderate acceleration, but it would be entirely ineffective against the extreme forces involved here. It is impossible to spread the pressure with enough uniformity to stop the liquefaction of soft tissues when the acceleration reaches hundreds or thousands of Earth gravities. Generation ships get around this issue by accelerating with incredible slowness over many decades. The body is never subjected to dangerous forces because the gentle thrust is applied over the course of years. This method works, but it requires centuries of travel time, trading deadly acceleration for a glacial pace. Suspended animation is another potential solution, but the process of freezing human tissue leads to the formation of ice crystals that tear cells apart. Despite decades of research, cryogenic preservation remains in the realm of theory. Even if it were perfected, thawing a person after a journey of high acceleration might only yield a thoroughly scrambled corpse. This points to a fundamental barrier for rapid conventional interstellar travel. One simply cannot accelerate human bodies fast enough to reach a significant fraction of light speed within a single lifetime. The laws of physics are unforgiving, and biology has limitations that technology cannot erase. The warp drive offers a solution that is both complete and remarkably elegant. A craft nestled within the bubble does not accelerate in any conventional sense. It experiences zero g-forces. There are no inertial effects whatsoever because the ship itself is not truly moving. Instead, space is moving around it, while the vessel remains locally stationary. A cup of coffee on a table would remain perfectly still. The human body would feel no stress at all. This is not a work of magic, but rather one of geometry. Inside the bubble, the local fabric of space-time remains completely flat and normal. All of the extreme curvature is confined to the bubble's boundary. The ship exists within an island of calm reality as the cosmos rearranges itself around it. The acceleration is applied to space itself, not to the vessel. In theory, a ship could go from a complete standstill to 10 times the speed of light in an instant, with zero physical sensation for anyone on board. For those inside the bubble, the transition would be entirely imperceptible. There would be no crushing forces and no gradual build-up of speed, just an instantaneous change in velocity without any of the effects normally associated with it. The reality inside the ship stays constant, while its relationship to the reality outside is transformed. This quality makes warp travel not just fast, but also comfortable and safe from the perspective of acceleration. Fragile equipment would not need any special mounting. Delicate scientific experiments could be conducted during the journey. Passengers would be free to walk around, share meals, and engage in normal activities, all while traveling faster than light. The voyage could become something almost routine, rather than a grueling test of endurance. These implications reach far beyond simple comfort. It would be possible to transport anything, no matter how delicate. Living organisms, complex machinery, and volatile chemicals could all be moved without any special preparations or reinforcement against the forces of acceleration. This opens up possibilities for interstellar colonization that would be unthinkable with conventional propulsion. One can imagine sending an entire ecosystem to a new homeworld, a collection of plants, animals, and microorganisms all journeying together in a balanced, self-contained habitat. With traditional rockets, keeping such a complex system alive through decades of travel, including phases of violent acceleration, seems nearly impossible. With a warp drive, it becomes a far more straightforward proposition. One would only need to maintain life support for what would feel like a brief and smooth trip. These advantages build upon one another. Warp drives promise speed without time dilation, movement without acceleration, and travel without the need for exotic life support or suspended animation. It seems that every problem that makes conventional interstellar travel so profoundly difficult simply vanishes inside a warp bubble. Of course, none of this becomes relevant until we can actually construct one. The interior of a functioning warp bubble would feel completely ordinary. There would be no way to tell whether the bubble was moving at 10 times the speed of light or sitting perfectly still. The laws of physics inside would operate exactly as they do on Earth, because the space-time within remains flat and undistorted. The extreme warping occurs only at the boundary, which acts as a protective shell around a pocket of normal reality. A watch on your wrist would tick at the same rate as a watch back on Earth. Your cells would age at a normal pace. Chemical reactions would happen at their standard speeds, and light would travel at its usual velocity relative to the bubble's interior. Nothing about the fundamental constants of physics would seem to change. You would exist in a small piece of normal space-time that just happens to be moving through the wider universe. This very isolation from external reference frames, however, does present its own interesting set of challenges, particularly when it comes to communication. Any radio transmission attempting to leave the bubble would face a formidable obstacle at its boundary, where space-time is intensely curved. This transition zone could prove entirely opaque to electromagnetic radiation, effectively blocking all conventional forms of communication. A vessel in transit would be completely isolated, unable to send or receive information until it finally decelerated from warp speed. Such a blackout period might last for days or even weeks, depending on the vast distances being covered. Consequently, mission planners would need to design for total autonomy, equipping ships with all necessary data and decision-making authority, as real-time contact with a home base would be impossible. The view from any window would present a profoundly alien spectacle. Light from stars in the direction of travel would be dramatically blue-shifted, its wavelength compressed so severely that it would become gamma rays. In the opposite direction, light from stars left behind would be red-shifted, stretched into the realm of radio waves by the expansion of space. The visible universe would shrink to a narrow, distorted ring encircling the ship's path, offering a smeared and warped glimpse of the cosmos. Some theoretical models even propose that the forward-facing windows might show nothing but darkness. The extreme compression of space ahead could generate an effect similar to an event horizon, where light is unable to escape the warp field and reach an observer's eyes. The crew might have to navigate entirely by instruments, flying blind through the interstellar void. Inside the ship, however, the environment would remain perfectly stable. The bubble's boundary would serve as a shield against all external conditions, from the faint glow of the cosmic microwave background to impacts from interstellar dust. It would provide protection from any conceivable hazard in deep space. A ship could, in theory, travel directly through a supernova, and its crew would experience none of the intense heat or radiation, safe within their protected pocket of space-time. The gravitational field inside would be whatever the ship's internal systems were designed to create, or it would be zero if no artificial gravity was engaged. The warp field itself generates no gravitational effects within the bubble because the space-time there remains flat. This is a crucial distinction from natural gravity wells, where the curvature of space-time produces tangible effects throughout the region. From the crew's perspective, all of the ship's energy systems would operate just as they were designed to. Fusion reactors, antimatter containment fields, and power distribution grids would all function normally. The truly exotic physics, the immense energy requirements, are confined exclusively to the boundary where space-time transitions from its normal state to its warped configuration. The greatest challenge of such a journey might ultimately be psychological. The experience of being isolated in a small bubble of familiar physics, while the universe itself is being restructured all around you, could be deeply unnerving. For some astronauts, the knowledge that they exist in a tiny pocket of reality, completely insulated from the greater cosmos, might induce a profound existential anxiety. Others, however, might find the feeling comforting, like being in a safe haven amid the vast and strange emptiness of space. Training protocols would have to place a heavy emphasis on maintaining routine and ensuring psychological stability during what would amount to a form of sensory deprivation from the external universe. While the trip itself might be relatively short, the experience of being so fundamentally disconnected from normal space-time could pose unexpected challenges to mental health. Still, when this is compared to the alternative of spending decades on a conventional spacecraft, slowly crawling between the stars and aging differently from everyone back home, a few weeks inside a comfortable warp bubble seems vastly more desirable. The psychological hurdles appear manageable, and the advantages offered by the physics would be revolutionary, if we can ever build it. This brings us to the question of who might already be trying. For years, NASA's Advanced Propulsion Physics Laboratory operated quietly under the direction of Harold White. It was tucked away in Building 9 at the Johnson Space Center in Houston. The lab's official mission statement sounded rather mundane, involving the study of exotic propulsion concepts for potential future applications. The unofficial reality, however, was that it was engaged in active warp drive research, funded through carefully worded budget requests. White's team constructed specialized equipment capable of measuring nanoscale spacetime distortions. They conducted experiments with various capacitor arrangements in an attempt to amplify Casimir effects. They also ran countless simulations to explore the most optimal geometries for a warp bubble. All of this work proceeded with caution and methodical precision, always maintaining plausible scientific cover stories for anyone who might ask uncomfortable questions. Then, an announcement in 2021 suggested the detection of warp bubble signatures within the laboratory. Suddenly, the quiet work was thrust into the public sphere. The ensuing media coverage compelled NASA to either disavow the research or formally acknowledge its legitimacy. The agency chose a middle path, confirming that the research was indeed taking place while stressing its extremely preliminary nature and the decades-long timeline to any potential applications. Behind closed doors, however, funding for the project reportedly increased. More physicists were brought onto the team, and orders for new equipment expanded. The laboratory that had once barely existed in an official capacity now had multiple research tracks running in parallel. One of these tracks focused on gaining a more complete understanding of the Casimir effect. Another explored the development of metamaterials that might be able to manipulate vacuum energy. A third line of inquiry investigated whether quantum entanglement could play a role in the process of warping space-time. Soon, other NASA centers became involved. The Glenn Research Center in Ohio contributed its deep expertise in propulsion systems. The Jet Propulsion Laboratory in California brought its advanced engineering capabilities to the table, and the Ames Research Center provided its powerful computational modeling resources. A research network quietly began to spread across multiple facilities, with each one working on a different piece of the larger, complex puzzle. The layers of government classification add another level of murkiness to the situation. It is highly likely that some warp drive research is being conducted behind the shield of security clearances, invisible to public oversight. If any breakthrough discoveries were to occur within these classified programs, we might not learn of them for years or even decades. The military applications of faster-than-light travel are so obvious that defense agencies are almost certainly funding their own parallel research efforts. The Department of Energy is also likely a participant, given the extreme energy requirements involved. Their national laboratories possess unparalleled expertise in plasma physics, fusion reactions, and high-energy particle interactions. If the generation of exotic matter ever proves to be possible, it is the DOE facilities that would be best positioned to make the attempt. International collaboration on this topic remains limited due to security concerns. NASA shares some of its basic research results with allied space agencies, but any work that begins to approach a practical application is immediately locked down. No nation wants to hand a potential adversary such a massive technological advantage. The first country to achieve a working warp drive would dominate not only space exploration, but potentially global warfare as well. This reality creates an unfortunate climate of secrecy around a field of research that humanity as a whole could greatly benefit from sharing openly. It's a quiet reality that researchers at institutions across the globe are likely working in parallel, grappling with identical obstacles that a more collaborative approach could overcome much faster. Geopolitical circumstances, however, tend to prevent open cooperation on any research with potential military sensitivity. Instead, hints occasionally emerge from those with inside knowledge. Presentations at conferences sometimes make reference to unexplained anomalies that have appeared in propulsion experiments. Patent filings can be seen describing exotic techniques for manipulating spacetime, though they are often framed in ambiguous terms. In their talks, researchers may carefully navigate around classified information while still signaling that much more is occurring than official statements would suggest. This raises the question of just how close an agency like NASA might truly be to a functional prototype. The public stance is that practical warp drives are a concept for the distant future, perhaps achievable in 50 to 100 years if research is sustained. In private, however, some scientists propose that breakthroughs could materialize far sooner, provided certain critical hurdles can be cleared. The disparity between these two timelines could conceal classified advancements, or it might simply represent the gap between conservative institutional projections and the optimism of scientific hope. What seems undeniable is that serious, well-funded research is underway at a number of government facilities, employing ever more sophisticated tools and methods. The very idea of warp drives has transitioned from the realm of science fiction into a subject of legitimate, government-funded physics. This shift alone marks enormous progress, regardless of how far we remain from any practical application. Yet government laboratories are no longer the only organizations pursuing this ambitious goal. While Elon Musk seldom discusses warp drives in public, the long-range plans for SpaceX, including Mars colonization and beyond, imply that someone there is considering faster methods of propulsion. The company's Starship program is designed to create self-sustaining cities on Mars, but in Musk's vision, Mars is just an initial foothold. He has stated on numerous occasions that for humanity to become a multiplanetary species, reaching other star systems is an eventual necessity. SpaceX is home to some of the world's foremost propulsion engineers and theoretical physicists. Their facilities in Hawthorne, Boca Chica, and Cape Canaveral contain advanced laboratories fully capable of conducting cutting-edge research. Moreover, the company's internal culture actively promotes ambitious, moonshot thinking and rapid prototyping. If any private entity were to seriously undertake warp drive research, SpaceX would be at the top of that list. Concrete details, however, are sparse. SpaceX guards its proprietary research with the same diligence as classified information, disclosing only what serves a strategic purpose. Still, job postings can sometimes hint at studies into exotic propulsion. Engineers with expertise in plasma physics, quantum field theory, and general relativity are recruited for unspecified advanced projects. Records of equipment acquisitions show purchases of specialized sensors and high-energy systems that have no clear application in conventional rocket development. Rumors also circulate about clandestine test sites in remote areas, where unusual experiments might be conducted away from public view. A few former employees have spoken of research tracks that explored physics beyond the scope of chemical rockets, though non-disclosure agreements keep them from sharing specifics. One anonymous source even alluded to the study of space-time manipulation techniques, but this claim could not be verified. The ecosystem of Musk's other ventures could also play a significant role. The Boring Company's proficiency in subterranean construction could be used to build shielded facilities for potentially hazardous high-energy experiments. Technology from Tesla, particularly in batteries and power management, might provide the precise energy control required to generate a warp field. Neuralink's work on brain-computer interfaces could one day assist in managing the immense computational loads needed for real-time warp field adjustments. The financial means available to Musk, both personally and through his companies, eclipse the research budgets of most governments. SpaceX already generates billions in revenue from its Starlink satellite launches and contracts with NASA. This income could readily finance speculative physics research if Musk were to decide the potential return justifies the risk. He has shown a consistent willingness to invest in long-shot technologies that many others have written off as impossible. It is presumed that Blue Origin, the space company founded by Jeff Bezos, is engaged in similar research. Bezos holds a long-term vision of an expanded human presence in space that mirrors Musk's own. Blue Origin has its own roster of talented engineers and physicists who have access to considerable resources. While their New Glenn rocket and lunar lander programs generate revenue, more speculative projects are likely proceeding quietly behind the scenes. Other major aerospace firms, such as Lockheed Martin, Boeing, and Northrop Grumman, all have advanced concepts divisions dedicated to exploring exotic propulsion. These groups operate with less public visibility than SpaceX, but are probably investigating similar lines of inquiry. Their relationships as defense contractors provide them with access to classified government research and funding for speculative work. It's also possible that Silicon Valley billionaires with a fascination for space are funding independent research groups. The breakthrough initiatives, sponsored by Yuri Milner, are already funding projects that search for extraterrestrial life and develop interstellar probes. One of these, Breakthrough Starshot, has a goal of sending tiny, laser-propelled spacecraft to Alpha Centauri at 20% of the speed of light. Such initiatives clearly show a readiness to fund revolutionary concepts in propulsion. Private research has the advantage of bypassing some of the bureaucracy and classification rules of government work, which can allow for faster development and greater risk-taking. On the other hand, it often lacks the deep institutional knowledge, extensive facilities, and collaborative networks that government labs can offer. An ideal scenario might involve a partnership between the public and private sectors, but such arrangements are often complicated by intellectual property rights and security classifications. What is evident is that numerous well-funded organizations, not just NASA, are actively pursuing research into faster-than-light travel. A race has begun, even if it is conducted largely in secret. The entity that achieves the first breakthrough stands to gain incomprehensible wealth and influence, or to usher in a new age of space exploration that will transform humanity. Perhaps it will be both. The real question now is which of the three principal approaches to warp drive technology will be the first to prove successful. Three different warp drive concepts have risen to the forefront as the most viable candidates for actual development. Each one addresses the same fundamental challenge from a unique angle: how to bend space-time to allow for travel faster than light without depending on impossible materials or infinite amounts of energy. The most widely known of these is the Alcubierre drive. This concept involves creating a bubble of space-time that contracts in front of a vessel and expands behind it, producing a wave that propels the ship forward. Recent theoretical refinements by Harold White and others have managed to reduce the immense energy requirements quite dramatically. The central difficulty involves creating sustained effects from exotic matter or negative energy density on a scale large enough to contain a spacecraft. One promising area of research explores whether cascading Casimir effects might be magnified through resonant phenomena. The idea is that if standing waves of negative energy density could be made to reinforce one another, their cumulative effect could reach a useful magnitude, even if the individual forces are infinitesimal. The principle is not unlike the way an opera singer can shatter a wine glass by amplifying small vibrations into a destructive force through acoustic resonance. The Notario drive presents a potentially more stable alternative, proposing smoother distortions of space-time rather than the sharp boundaries that demand intense concentrations of energy. This model distributes the warping effect over a much larger volume. Such a distribution might be achievable with precisely configured electromagnetic fields or plasma arrangements that generate the required energy density gradients, possibly without needing any exotic matter. At several universities, researchers are investigating whether toroidal plasma containment systems, similar to miniature fusion reactors, could produce Notario-style warp fields as a secondary phenomenon. In this scenario, the plasma itself could supply the variations in energy density needed to bend space-time, though achieving the necessary level of control remains a formidable challenge. A third, less discussed but potentially transformative approach centers on the direct manipulation of dark energy. Accounting for 70% of the universe's total energy density, dark energy exhibits negative pressure characteristics that are conceptually similar to what a warp drive requires. If it were possible to locally concentrate or otherwise influence dark energy, we might be able to generate warp effects without exotic matter or Casimir amplification. The primary obstacle, however, is our profound lack of understanding of what dark energy actually is, let alone how to control it. Current physics cannot account for its origin or predict its behavior beyond its observed influence on cosmic expansion. Learning to harness it would necessitate fundamental breakthroughs in our understanding of the universe. Yet, the implications of success would be profound, as an infinite energy source with exotic properties already permeating all of space could be the very fuel a warp drive needs. Some scientists are now proposing hybrid models that combine elements from all three of these concepts. Such a design might use an Alcubierre-style oscillating bubble geometry for greater energy efficiency, incorporate Notario-style smooth boundaries for stability, and rely on dark energy manipulation for its power source. The optimal solution may emerge from a blend of insights drawn from multiple models, rather than a rigid adherence to a single approach. These various concepts are under constant evaluation through computer simulations, which explore vast parameter spaces to identify workable combinations. Supercomputers perform millions of iterations, testing different bubble shapes, energy distributions, and field configurations. This process is analogous to pharmaceutical research, where countless molecular variants are tested in the hope of finding one with the desired therapeutic effects. Laboratory experiments, however, are far behind these simulations, as constructing the equipment needed to test for warp field generation is extraordinarily difficult. Measuring nanoscale spacetime distortions requires instruments that push the very limits of our current technological capabilities. To scale these experiments up to even millimeter-sized effects would require entirely new kinds of apparatus that do not yet exist. Progress in this field is therefore incremental. Each small success in the lab helps to validate parts of the theory and illuminates potential paths forward. Each simulation helps to identify promising parameter ranges or reveals dead ends that should be avoided. Slowly, the field advances from the realm of pure speculation toward the possibility of engineering. No one can say which approach might prove successful first, or if an entirely different concept will emerge and surpass them all. The competition among these different designs is a powerful driver of innovation, as research groups pursue distinct strategies, each hoping theirs will be the one that works. This diversity of effort increases the overall probability that someone, somewhere, will discover a configuration that is truly functional. But every one of these approaches ultimately confronts the same fundamental challenge. Manipulating the fabric of space-time itself demands a deeper understanding of physics than we currently possess. Classical physics once described the universe as a kind of clockwork mechanism. In this view, particles had definite positions and velocities, while forces acted predictably according to clear mathematical laws. Everything was, in principle, calculable and deterministic. With perfect knowledge of the initial conditions, one could predict the future with absolute accuracy. This worldview was the bedrock of science for centuries. The arrival of quantum mechanics, however, upended that comfortable certainty. At the microscopic scale, particles exist not in precise locations but as fuzzy clouds of probability. They exhibit the characteristics of both waves and particles at the same time. The act of measuring one of their properties introduces a fundamental uncertainty into other properties. The universe, it turns out, operates on principles of probability and randomness rather than clockwork precision. Even more strangely, quantum mechanics showed that empty space is not truly empty. It is a roiling sea of virtual particles that constantly emerge from and disappear back into nothingness, borrowing their existence from quantum uncertainty. This churning quantum foam underpins all of reality, producing measurable effects even though the particles themselves are undetectable. The Casimir effect is direct proof of this reality. Those metal plates, which appear to attract one another in defiance of classical physics, are actually being pushed together by imbalances in the quantum vacuum fluctuations around them. The microscopic reality of our universe does not conform to the intuitive rules that govern our everyday lives. This strangeness is not an anomaly but an essential feature of reality, Warp drives are an attempt to exploit this inherent quantum strangeness. They depend on manipulating the energy of the quantum vacuum to generate regions of negative energy density. This requires an ability to understand and control quantum phenomena at scales and intensities far beyond our current reach. We would need to make quantum effects macroscopic and sustained, rather than microscopic and fleeting. While quantum field theory provides the mathematical language for these ideas, its application to practical engineering remains largely an aspiration. The calculations become impossibly complex when applied to scenarios involving curved spacetime and powerful gravitational fields. Physicists can formulate the equations, but they cannot yet solve them for realistic conditions. Supercomputers offer assistance, but they still cannot fully model the dynamics of a warp drive from a quantum mechanical perspective. This gap between theoretical understanding and practical application represents one of the greatest obstacles to developing a functional warp drive. We know that quantum effects must be part of the solution. A curious gap exists between our knowledge of the relevant principles and our ability to design systems that truly function. We are missing both the computational tools and the necessary physical intuition. The situation is reminiscent of an attempt to construct computers during the 1800s. The fundamental physics was known, yet the engineering expertise required for practical application was still centuries in the future. However, recent progress in the field of quantum computing may offer a path forward. These machines leverage the very same peculiar behaviors that render quantum mechanics so contrary to our everyday experience. Their potential lies in their ability to model phenomena like quantum vacuum effects and the curvature of space-time with a level of efficiency that conventional computers cannot match. If these quantum systems can accurately simulate the dynamics of a warp field, they could potentially uncover viable configurations that classical methods might overlook. The concept of quantum entanglement introduces another layer of profound possibility. Particles that are entangled seem to influence one another instantly, regardless of the distance separating them, in a way that appears to defy the universal speed limit of light. It was a phenomenon Einstein found so unsettling, he famously described it as spooky action at a distance. Modern experiments have repeatedly verified that this connection is real, although careful analysis confirms that no information is actually transmitted faster than light via entanglement. The question then arises, could entanglement have a role to play in the mechanics of a warp drive? Some speculative frameworks propose that entangled quantum states stretching across the boundary of a warp bubble could permit the transfer of information from the inside to the outside, even with the intense distortion of spacetime. Other theories suggest using entanglement to orchestrate the manipulation of the quantum vacuum over vast areas, thereby generating coherent warp fields. It must be said that these concepts remain highly conjectural, approaching the realm of science fiction. Yet, the history of quantum mechanics is filled with examples of reality, operating on principles far stranger than our common sense would allow. To dismiss ideas simply for sounding impossible has proven to be a misguided approach when engaging with quantum phenomena. The shift from classical to quantum perspectives represents a philosophical evolution as much as a scientific one. It requires an acceptance that the universe, at its most fundamental level, is governed by probabilistic rules that we cannot intuitively visualize. The pursuit of warp drives compels us to venture deeper into this quantum domain, a place where phantom particles and indeterminate properties somehow work in concert to produce macroscopic results. Attaining the same level of confidence in engineering quantum phenomena as we have with classical mechanics could require many decades, or perhaps even centuries. The potential rewards, however, extend far beyond warp drives, hinting at entirely new technologies built upon the manipulation of reality's quantum foundations. We are poised at the beginning of a new era in physics, and the solution we seek might already be present, concealed within the most mysterious corners of the cosmos. Dark energy stands as one of the most profound enigmas in all of physics. Astronomical observations reveal that the expansion of the universe is accelerating, propelled by an unknown form of energy that seems to permeate all of space. This dark energy is estimated to constitute 70% of everything in existence. Despite its prevalence, we are unable to detect it directly. We do not know its nature, and our ideas about its properties are vague at best. What is known, however, is deeply intriguing. Dark energy displays a negative pressure, an effect that pushes space apart rather than drawing it together as ordinary matter and energy do. This characteristic of negative pressure is precisely what a warp drive requires to operate. If it were possible to concentrate or manipulate dark energy on a local scale, it could serve as the exotic fuel needed to create warp bubbles, eliminating the need for impossible materials. While this may sound like magic, it is important to consider that dark energy is already ubiquitous. We are immersed in it at this very moment. Every cubic meter of what appears to be empty space contains a minute quantity of this energy. In a sense, the universe has graciously supplied an infinite source of fuel with the exact exotic properties that a warp drive demands. The challenge is simply learning how to tap into it. Modern physics offers no explanation for the origin of dark energy or the source of its negative pressure. The prevailing theories speculate that it could be an intrinsic property of space-time itself, a cosmological constant that signifies the energy density of the vacuum. Alternative hypotheses propose that it is a dynamic quantum field that is evolving slowly over cosmic timescales. No one can say for sure. This profound lack of understanding makes the prospect of its manipulation seem incredibly remote. After all, how can one control something that is not understood? And yet, history is replete with examples of humanity harnessing phenomena long before achieving a full comprehension of them. Ancient civilizations used fire for millennia before the chemistry of oxidation was discovered. For 10,000 years, farmers selectively bred crops before the principles of genetics were known. Practical application can, and often does, precede complete theoretical insight. What if the generation of a warp bubble could inadvertently draw upon dark energy? The space-time distortions produced by a warp field might naturally tap into the dark energy that permeates that specific region of space. The bubble, in this scenario, would be powered by the very same mysterious force that is accelerating the expansion of the entire universe. This would provide an elegant solution to the exotic matter problem by utilizing an energy that already exists, rather than attempting to generate it artificially. A number of theoretical models are now exploring whether warp bubbles could create zones where dark energy becomes concentrated or behaves in an unusual manner. The intense curvature of space-time at the bubble's edge might locally alter how dark energy manifests. If conditions could be created where dark energy temporarily exhibited an even more potent negative pressure, this amplification might be sufficient to produce the warp effect. There is also the possibility that quantum vacuum energy, the force behind the Casimir effect, is connected to dark energy. Both concepts involve energy densities within seemingly empty space, and both exhibit qualities that classical physics failed to predict. A deeper understanding of one could very well shed light on the other. If Casimir-style vacuum manipulation can be scaled up to useful dimensions, we might find that we are simultaneously learning how to influence dark energy. The most significant obstacle is detection. We are aware of dark energy's existence because we can measure its influence on cosmic expansion, but to detect it locally with our current instruments is impossible. The challenge is analogous to trying to measure minuscule currents while standing in the middle of the ocean. Any local fluctuations are completely overwhelmed by the cosmic scale averages. A formidable technical hurdle is the development of sensors sensitive enough to measure variations in dark energy density within a laboratory environment. Some researchers have suggested searching for signatures of dark energy within gravitational wave data. In the same way that warp bubbles are theorized to produce distinct gravitational waves, fluctuations in dark energy might also generate their own unique patterns. The advanced detectors scheduled to come online in the next decade could possess the necessary sensitivity to measure such effects. If we could accurately map the distribution of dark energy, we might uncover natural concentrations or voids that could reveal techniques for its manipulation. It may be that regions near black holes or neutron stars display unusual dark energy behavior that warrants closer investigation. It is possible that the universe has already put the manipulation of dark energy on display within its most extreme environments. While this avenue of research is profoundly speculative, the potential rewards are significant enough to merit serious investigation. If humanity could ever learn to access it, dark energy would represent a truly vast, untapped reservoir of power. For the specific challenge of warp drives, this could be the key that transforms an impossible feat of engineering into one that is merely extraordinarily difficult. The cosmos may have already provided the very fuel we require. The task remaining is to discover how to access it. Albert Einstein gave us a picture of space-time as a smooth, continuous fabric that stretches throughout the universe. In this model, massive objects create depressions in the material, while accelerating masses generate ripples that travel outward as gravitational waves. This has remained an elegant and guiding concept in physics for more than a century. But an intriguing question arises. What if space-time is not perfectly smooth? What if it possesses seams, boundaries, or discontinuities where the fundamental rules are altered? Insights from quantum mechanics suggest that at the very smallest scales, space-time might have a granular texture. The Planck length, approximately 10 to the minus 35 meters, is thought to represent the smallest distance that holds physical meaning. Below this threshold, quantum fluctuations would cause the idea of a smooth space-time to break down entirely. Reality could be pixelated, much like a digital screen, appearing continuous only from a great distance. These quantum grains of space-time might represent the very seams in the fabric, points where manipulation could be easier or where different phenomena might occur. If creating a warp drive requires the tearing or stitching of space-time, it would be logical to search for natural seams where the fabric is inherently weaker. The concept is similar to how a tailor prefers to cut cloth along its weave, rather than struggling against the grain. Black holes offer the most dramatic examples of space-time boundaries known to science. The event horizon is a stark dividing line, a threshold beyond which physics undergoes a fundamental shift. Inside this boundary, the roles of space and time effectively interchange. Escape is no longer possible, and the flow of time is directed not toward the future, but toward the singularity. Studying these natural boundaries could teach us a great deal about how to create the artificial edges needed for a warp bubble. Hawking radiation, for instance, is a phenomenon that arises from quantum effects right at the event horizon, where virtual particle pairs are separated by the intense gravity. One particle is pulled into the black hole while its partner escapes, resulting in what appears to be faint radiation emanating from the object. This is a clear demonstration that extreme space-time curvature can give rise to unusual quantum effects, and the boundaries of a warp bubble might function by leveraging similar principles. Wormholes, should they exist, would be the ultimate space-time seams. They represent a shortcut connecting two distant regions, forming a tunnel through the fabric of reality itself. According to theoretical models, keeping a wormhole open would necessitate the presence of exotic matter, the very same kind of substance required for a warp drive. This has led to the idea that a warp bubble could be, in essence, a mobile and self-contained miniature wormhole, ferrying a small pocket of normal space-time across the wider cosmos. String theory introduces another fascinating possibility, that space-time has more dimensions than the three of space and one of time we experience. These extra dimensions are thought to be curled up so tightly that they are undetectable to us. However, under conditions of extremely high energy or immense curvature, they might become accessible. It is conceivable that a warp drive, operating at the boundaries of space-time, could tap into these hidden dimensions. Some physicists are also exploring whether space-time has an underlying microstructure, analogous to how liquid water's properties emerge from the behavior of individual H2O molecules. If space-time is an emergent phenomenon arising from something more fundamental, then understanding that substrate could unlock new methods of manipulation. Theories like loop quantum gravity propose that space-time is not continuous at all, but is instead woven from discrete quantum loops or networks. From this perspective, a warp drive begins to seem more plausible. If space-time is made of component parts, one might be able to disassemble it and then reassemble it in a different configuration. The fabric would not be a single, indivisible sheet, but a weaving that could be unraveled and rewoven into the patterns that produce warp effects. This would, of course, demand a technology capable of manipulating the fundamental building blocks of spacetime, whatever they may be. Cosmic strings, which are hypothetical defects in spacetime left over from the early universe, would serve as natural seams on a galactic scale. These one-dimensional objects, possessing enormous mass density, could stretch across entire galaxies. If they are real, and if we could locate them, they might reveal how space-time defects behave and whether they could be created artificially. All of these concepts remain highly theoretical. We do not yet know if space-time truly has seams, grains, or an underlying structure, The smooth fabric model may be perfectly accurate. Even so, exploring these alternatives opens up new avenues of thought for the physics of warp drives. If spacetime is more complex than Einstein envisioned, it may also prove to be more malleable. The critical step is to find where the fabric of reality might already be weak or structured in a different way. Such locations could serve as natural laboratories for testing space-time manipulation, or as sites where generating a warp field becomes more feasible. The universe might have already left clues about how to reshape it, if only we know where to look. This brings us to the most important consideration of all. How close are we, really? With every new breakthrough, new timelines and predictions emerge. Optimists suggest that if research maintains its current pace, working warp drive prototypes could appear within 10 to 15 years. Pessimists, on the other hand, argue that practical applications are still centuries away. The reality is likely somewhere in between these extremes, but closing that gap requires a clear understanding of the specific problems that are still unsolved. The generation of energy is the most immediate challenge, even with optimized designs and reduced power needs. A warp drive requires a colossal amount of power that must be controlled with incredible precision. While current fusion research is making steady progress, it has yet to achieve a sustained net energy gain. The production of antimatter continues to be exceptionally slow and prohibitively expensive, and the manipulation of dark energy exists only in theoretical papers. Creating a negative energy density on a useful scale presents an even more difficult problem. The work by White's team detected a nanoscale warp geometry, but scaling that up by a factor of 10 billion is a monumental task. The Casimir effect, a potential source, weakens very quickly with distance, and any techniques to amplify it remain purely speculative. Without a major breakthrough in the manipulation of the quantum vacuum, this single obstacle could delay a practical warp drive for many decades. Materials science also faces extraordinary demands. Any spacecraft enveloped by an intense warp field would be subjected to stresses and radiation far beyond what any current materials can endure. The structure of the ship would need to remain perfectly stable while spacetime is being violently contorted just meters away. Developing materials that can survive these conditions will require extensive testing, which ironically cannot even begin until we can generate the very warp fields we need to test them against. The very principles of navigation and control would require a complete reinvention. Guiding a vessel whose destination is invisible presents an immense challenge, as does the problem of avoiding collisions when moving beyond the speed of light. The question of what might occur during a malfunction inside a warp bubble traveling at 10 times light speed raises safety concerns of an entirely new magnitude. Before any rudimentary mission could be considered even remotely safe, these engineering hurdles demand robust solutions. Gaps also persist in our theoretical physics, making predictions uncertain. We do not yet possess equations that can fully simulate the dynamics of a warp drive. The quantum effects that might occur at the boundaries of the bubble are still not well understood. It also remains unknown whether dark energy could be an asset, or if it might introduce entirely new complications. Each one of these uncertainties could conceal an insurmountable obstacle that might only reveal itself during an actual attempt at construction. While international collaboration could certainly speed up development, such partnerships seem improbable due to prevailing national security interests. If a major breakthrough were to happen at a classified facility, commercial uses could trail military applications by years or even decades. The first functioning warp drive might therefore be a secret military program, its existence unknown to public science for a very long time. The level of financial commitment is, of course, a critical factor in this equation. Current research into warp drives operates with budgets in the millions annually, spread across all global programs. By comparison, fusion research is funded with billions. The Manhattan Project cost the equivalent of $27 billion in today's currency over just 4 years, while the Apollo program consumed $150 billion. If humanity were to dedicate similar resources to warp drive technology, a timeline of 10 years could potentially be within reach. Without that kind of commitment, progress is likely to remain slow. Some scientists privately concede that a single, pivotal breakthrough could alter the entire landscape overnight. If a researcher were to discover how to generate scalable negative energy density, or learn to manipulate dark energy, or stumble upon an entirely unforeseen method of space-time manipulation, the entire developmental timeline could contract dramatically. We might transition from barely measuring nanoscale effects to constructing test vehicles in only a few years. History provides many examples of technological revolutions happening far more quickly than experts had forecasted once. A key enabling discovery was made. Powered flight evolved from a near impossibility to a routine form of travel within 2 decades. Nuclear energy became a practical reality within 5 years of its theoretical conception. Computers, once the size of rooms, shrank to fit in our pockets over a span of 30 years. The right discovery can trigger an explosive cascade of progress. Conversely, some challenges prove to be far more stubborn than initially thought. Fusion energy, for instance, has famously remained about 30 years in the future for more than 6 decades. Quantum computing took many decades longer to develop than its early proponents had predicted. Certain technological barriers can persist with remarkable tenacity, resisting the efforts of brilliant minds and massive investment. The question then becomes, into which of these categories does the warp drive fall? The answer depends on whether the universe fundamentally permits the technologies we require. If reality allows for the generation of negative energy at scale, the efficient manipulation of dark energy, and the stable maintenance of a warp field, then the problem becomes a race of engineering. If, however, the universe has built-in protections that prevent these effects at useful scales, we may find ourselves pushing against the limits of physics indefinitely. The only way to know for sure is to continue moving forward by funding the research, building more sensitive instruments, conducting more experiments, and testing ever bolder theories. Somewhere, someone must find the key that unlocks the next level of physics. When that moment arrives, the real countdown will begin. Achieving faster than light travel is more than a technical milestone. It represents a fundamental transformation of humanity's potential. Every great migration in our history, from our origins in Africa to every continent and across oceans to new worlds, has expanded our horizons and compelled us to innovate and adapt. The stars are our next great frontier, but they are a frontier we can only explore if we can reach them. With warp drives, the galaxy would unfurl before us. Hundreds of potentially habitable planets, located within 50 light-years, would become accessible destinations. We could establish colonies on worlds far more suitable for life than Mars could ever be. Humanity would have the chance to spread across multiple star systems, which would help ensure our long-term survival, even if a catastrophe were to strike Earth. We would evolve from a species confined to a single planet and facing existential risks into a multi-world civilization defined by redundancy and resilience. The economic implications are staggering to contemplate. Asteroid mining would become a routine endeavor when the asteroid belt is just hours away. Rare elements that are abundant in other solar systems could be harvested and brought back. The energy resources available from other stars or gas giants vastly exceed anything Earth can provide. A spacefaring civilization with warp capability would command resources that would make our current global economy appear minuscule. The pace of scientific discovery would also accelerate dramatically. The direct study of alien ecosystems, close-up observation of stellar phenomena, and hands-on investigation of black holes and neutron stars would all become feasible. Fundamental questions about the origin of life, the formation of planets, and the evolution of the cosmos could be answered through direct observation rather than distant inference. Every new world we visited would rewrite our textbooks and challenge our assumptions. The prospect of encountering extraterrestrial civilizations becomes a tangible possibility, should they exist within our reach. Instead of waiting for centuries for radio signals to traverse the void, we could physically travel to nearby systems to search for life directly. We might discover the ruins of civilizations long extinct, encounter primitive forms of life, or perhaps make contact with an intelligence equal or even superior to our own. The implications this would have for philosophy, religion, and our very identity as humans would be profound. A cultural transformation would also seem inevitable. A humanity distributed among the stars would likely diversify in ways we can scarcely predict. Isolated colonies would develop their own unique customs, languages, and societies, each adapted to its own world. We might fragment into distinct branches of human civilization, or we could maintain our unity through rapid warp-speed communication and travel. Either path leads to futures that are radically different from our present reality. However, the risks involved cannot be overlooked. Warp drive technology could enable the creation of terrifying weapon systems. Any nation or group possessing this technology would hold an overwhelming advantage over those without it. Warfare in space could erupt on a scale that would make Earth's historical conflicts seem trivial. It is crucial that we develop frameworks to prevent militarization before the technology is fully realized, though history suggests such efforts are often unsuccessful. The environmental consequences also remain a significant unknown. Does repeated warp travel cause damage to the fabric of spacetime? Could we inadvertently destabilize regions of space through overuse? Is it possible that warp bubbles leave behind some form of pollution, or a side effect that accumulates to dangerous levels over time? These are questions we must investigate before deploying the technology on a wide scale. Finally, the ethical debates are certain to intensify. Who will be granted access to warp-capable ships? How can we prevent the exploitation of newly discovered worlds? There are profound questions that must be considered long before circumstances force our hand, demanding answers before a crisis requires a hasty decision. If we were to discover rudimentary life forms, what solemn obligations would we have to avoid interfering with their natural course of development? How should we approach the intricate rights of future human colonists who might desire self-governance, entirely independent of Earth? While these are complex dilemmas, the most significant transformation might ultimately be on the human spirit itself. The knowledge that we can journey to the stars would fundamentally alter our perception of our place in the cosmos, shifting how we think about our collective existence. We would cease to be a species imprisoned on a single, fragile planet and would instead become truly free to explore. This dramatic expansion of the possibility space for human achievement and direct experience could serve as a powerful inspiration for generations, much in the way the Apollo program captivated millions of people despite its relatively limited practical benefits. This specific moment in our history, as researchers make incremental progress toward the physics of a functional warp drive, may one day be viewed as the critical juncture when humanity's future trajectory was permanently reset. We either solve this immense challenge and become a civilization that travels between the stars, or we remain confined within our local solar neighborhood, perhaps indefinitely. The choice, in a very real sense, is not completely up to us. We can certainly fund the necessary research and push against all known boundaries, but it is the universe that ultimately decides if the fundamental laws of physics will permit what we need. Reality might simply not allow for the existence of warp drives, no matter how clever our efforts become, or it may have already provided all the necessary components, waiting patiently for us to find the specific combination that unlocks this incredible possibility. In either case, the attempt itself holds immense and undeniable value. Pushing against the frontiers of what is possible invariably expands the scope of human knowledge and technical capability. Even if the primary objective is never fully reached, the technologies that are developed in the dedicated pursuit of warp drives will inevitably produce spin-off applications that will benefit all of humanity in unforeseen ways. We always learn the most by attempting to do what seems, at first, to be impossible. The scientists working in laboratories today, who are meticulously measuring infinitesimal nanoscale distortions and running extraordinarily complex quantum simulations, are the trailblazers at the very edge of physics, exploring frontiers that might not yield practical results for decades. They operate on timelines that stretch far beyond individual careers, pursuing fundamental knowledge that may only serve the generations yet to come. It is precisely this kind of patient, long-term thinking that has built everything of lasting and profound value in our civilization. It is entirely conceivable that the person who solves this monumental puzzle is alive right now. Perhaps you are the engineer who will design the first scalable and stable negative energy generator, or the physicist who will finally crack the secrets of dark energy manipulation. You could even be the programmer who writes the elegant code that enables the real-time, intuitive control of a functional warp field. A breakthrough of this magnitude could emerge from anywhere, from any individual with enough deep curiosity and unwavering determination. The universe itself is of a scale that truly defies our comprehension. Light from the very edge of the observable cosmos has been traveling in our direction for over 13 billion years, and yet will never complete its journey because the fabric of space is expanding faster than light can cross it. We exist inside a tiny, isolated bubble of causally connected space, able to interact only with the limited cosmic region that light has had enough time to reach since the Big Bang. Warp drives would not change those ultimate cosmic limits. Even at a velocity of 1,000 times the speed of light, the observable universe would still take millions of years to cross. What they would do, however, is completely transform what is practically achievable for human civilization operating on human timescales. The nearby galaxy, containing its billions of potential worlds, would at last become an accessible destination. That is the true prize we are chasing. Not infinite reach or some form of godlike power, but simply the precious ability to explore our immediate cosmic neighborhood within the span of human lifetimes rather than across uncounted millennia. We hope to visit a few dozen nearby stars, to investigate the planets that our telescopes indicate look the most promising, and to establish a human presence among the stars while Earth always remains our cherished home. The race toward achieving 10 times the speed of light is therefore not just about science, or engineering, or even national prestige. It is about the fundamental question of whether humanity has a future among the stars or is destined to remain forever confined to this single planet, watching the cosmos from a distance we can never hope to bridge. That future is being written in laboratories right now. The next chapter of human history is taking shape one equation, one experiment, and one crucial breakthrough at a time, and it is quite possible that it will arrive sooner than any of us can currently imagine.